In this video, we are going to revise grade 11 trigonometric identities, proving identities, using the identities to simplify expressions, and then we are also going to just revise the trig graphs. Okay, so a trigonometric identity is a mathematical statement that is true for all values of the variable, excluding the values for which the statement is not defined. And in grade 11, we looked at two identities. The first was the quotient identity, which says that tan theta is equal to sine theta over cos theta, and this can also be applied to tan squared theta equals sine squared theta over cos squared theta. So just remember that. Now, the quotient identity has a fraction, and if the denominator is 0, it's obviously undefined. So wherever cos theta equals 0, this identity would be undefined. Now, cos theta is 0 at 90 degrees, and then if we add multiples of 180 degrees, it is 0 again. So this identity is undefined if theta equals 90 degrees plus k times 180 degrees, where k is an element of integers. Okay, then we have the square identity, which says that sine theta all squared plus cos theta all squared equals 1. And this can be rewritten in different ways depending on how we need it. So if I were to take this square identity and solve for sine theta squared, I would subtract cos theta squared, which leaves me with 1 minus cos theta squared. And likewise, if I were to take this square identity and solve for cos theta all squared, I would subtract the sine theta squared, and I'm left with that equaling 1 minus sine theta squared. So we have the quotient identity and the square identity, and the square identity can be rewritten in 3 different ways. Right, so just a reminder of what we did in grade 11 relating to trig identities. We derived the quotient and square identities. We used the identities to simplify expressions. We used it to prove other identities. And then we simplified using identities and reduction formulae. Okay, so we are going to focus on revising number 3 and number 4 here. So, proving identities. Now, proving identities takes a lot of practice, really just to get your eye in actually, because the more you practice, the more you see common elements, and then it makes it easier, okay? But there are certain tools that you really must have in your pocket. And the first is the identities. So we have the quotient identity and the square identity in all 3 forms that it can be written, okay? And then remember the algebra, okay? Now, if we have fractions in our identity, a very easy tip is to write those 2 fractions as 1 fraction by finding the lowest common denominator and simplifying, okay? Don't forget that. And then, of course, we can also factorize, and we have the highest common factor, square, difference of squares, trinomials, grouping, sum or difference of cubes. Sorry, this should be cubes. Okay, so when you have a fraction, remember, write it as 1 fraction, and of course we can factorize to manipulate our expressions. Okay, so let's look at examples. Example 1 says prove that. Okay, and we have 1 over cos theta squared minus 1 equals tan theta all squared. Now when you are proving identities, remember to split the identity into its left-hand side and the right-hand side, and what you need to do is prove that the left-hand side is equal to the right-hand side. Now to do that, you cannot start off with having the one side equal to the other side straight away. Okay, so split them up and start with one side and simplify it as far as you can until you either equal the other side, or if you can't equal the other side, you start working with the other side, say the right hand side, and simplify that, and you would end up with the same expression. Okay, so let's start with the left-hand side, which looks more complicated in this one. Sorry. Not sure what I did there. Okay, so left-hand side equals 1 over cos theta all squared minus 1. Okay, now I have a fraction minus another term. I've got two terms with a fraction. I'm going to write this as one fraction with a lowest common denominator, which in this case is cos theta all squared. Okay, so I've got 1 minus. Now to write 1 as a fraction with cos theta squared in the denominator, I have to multiply by cos theta squared. So I have 1 minus cos theta squared over cos theta squared. Okay, so I start off with two terms, one of which is a fraction. Then I write it all as one fraction. Okay, and looking at this, what I see is in my numerator, I have 1 minus cos theta squared. Now, that is the square identity, okay, which has the form sine theta squared equals 1 minus cos theta all squared. Okay, remember that it starts off with sine theta all squared plus cos theta all squared equals 1. If I solve for sine theta squared, I get this. So I know that 1 minus cos theta squared is equal to sine theta squared. So I replace the numerator with the sine theta squared. And I have sine theta squared over cos theta all squared. Okay, now sine over cos, that is the tan identity. So the quotient identity, was tan theta equals to sine theta over cos theta. And of course, we also have the squared form, which applies here. So this is equal to tan theta all squared, which is my right-hand side. So I finish off the proof by saying equals right-hand side. Let's do a second example. Again, I have to split up the identity that I have to prove into the left-hand side and the right-hand side and work separately with them, proving that the one is equal to the other. Okay, so the left-hand side looks more complex, so I'm going to start off with the left-hand side. You don't always have to start off with the left-hand side. You can, by all means, start with the right-hand side if it's complicated and you can work with it. Okay, so looking at this, I have two terms, one of which is a fraction, so I can definitely combine the fractions. But I also see that I have tan, cos, and sine. So that is 1, 2, 3 trig functions. Now, I would like to get rid of one trig function. Okay. Now, the only way I can get rid of it is if I replace it with something that it is equal to. Okay. Now, tan beta is the quotient identity. Tan beta is equal to sine beta over cos beta. So I'm going to replace tan beta with that. So it's sine beta over cos beta plus cos beta over 1 plus sine beta. Now I have a fraction plus a fraction. I'm going to write it all as one fraction with the lowest common denominator, which is cos beta times 1 plus sine beta. So every denominator is represented there. So let me just write that down. Okay, to change the denominator of the first fraction, I multiply by the bracket 1 plus sine beta. So I do the same to the top. To change the second fraction's denominator, I multiply by cos beta. So I'm going to do the same to the top. So I have cos beta times cos beta, which gives me cos beta all squared. Okay, simplifying this, so I'm not going to multiply out the denominator because my denominator in factored form is actually more useful because I'd like to be able to cancel factors if possible. But my numerator, I will multiply out the bracket because I'd like to simplify the numerator. So I have sine beta times 1, which is sine beta, plus sine beta times sine beta, which is sine beta squared, plus cos beta squared. And straight away, I see an identity that I can use. Okay, sine beta squared plus cos beta squared, that is the square identity, which is equal to 1. So in place of sine beta squared plus cos beta squared, I will write 1. So in the numerator, I now have sine beta plus 1 over cos beta times 1 plus sine beta. Wanting to simplify, I see that I have sine beta plus 1 and 1 plus sine beta in the numerator and the denominator. If I put this in brackets, it makes it a factor. Okay, so takes it from being 2 terms to 1 term, which means I can cancel. Now, they're not exactly the same because the terms are in a different order, but I can write terms in different orders as long as I take the sign in front of them along with them, and that they would be exactly the same, 1 plus sine beta. So I can cancel those factors, and I'm left with 1 over cos beta, which is equal to the right-hand side. And I finish off by saying that. Right. Now we revise simplifying expressions using identities and reduction formulae. So in this example, we are to simplify tan 225 degrees plus cos 180 degrees minus theta times sine 90 degrees plus theta, all divided by sine negative theta. Okay, first thing I notice is that I have a plus. Okay, so in the numerator I have 2 terms because terms are separated by plus or minus. Okay, so just take note of that. And of course we have reduction formulae going on here. Okay, and tan 225, we'll have to try reduce that to an acute angle. So a couple of things that we can try. So I'm just going to start off with reducing everything to an acute angle. Okay, so tan 225, the angle 225 is in the third quadrant, in which I write angles as 180 degrees plus the angle that would make this value equal to 225, which is 45. Okay, plus, going to the next trig function, cos of 180 degrees minus theta. This angle is in the second quadrant, in which cos is negative, so it reduces to negative cos theta. Okay, times sine 90 degrees plus theta. That is in the second quadrant, and I have a 90-degree angle, which means I'm going to go to the co-ratio. So sine is positive in the second quadrant, so it's going to go to positive cosine theta. And in the denominator, sine of a negative angle is always negative sine of the positive angle. Right, simplifying further, tan 180 degrees plus 45. In the third quadrant, tan is positive, so that reduces to tan 45 degrees. Okay, and multiplying this out, I have minus cos theta all squared, all divided by negative sine theta. Okay, now, so tan 45 degrees, 45 is a special angle, and tan 45, if you remember your special angle triangles, you might actually just know the value for 45, tan 45, which would be good. Okay, in case you don't, remember 45-degree angle, tan is opposite over adjacent, which is 1 over 1, which is 1. But tan 45 you might also easily know from the tan graph. Okay, so I have 1 minus cos theta squared divided by negative sine theta. Now, looking at this, I recognize the square identity. Okay, remember sine theta all squared plus cos theta all squared equals 1. If I solve for sine theta all squared, by subtracting cos theta, I'm left with 1 minus cos theta all squared. This is what I've got here, okay? So I can replace it with the sine theta squared divided by negative sine theta. Now remember that sine theta all squared is sine theta all squared like that. So it's actually a sine theta times a sine theta. So if I'm dividing by sine theta, I can actually cancel one of the sine thetas, and I'm left with sine theta in the numerator divided by negative 1. So that's just negative sine theta. A second example, we are to simplify cos 140 degrees all squared minus tan of 40 degrees all squared times cos 220 times sine 50. Okay, so looking at these angles, first of all, I notice that we have a minus, which means I've got two terms, okay, and then I notice that the angles are all different, okay, so I can't cancel anything. I don't see any immediate identity that I could apply. So what I will do is reduce everything to an acute angle and see if we can simplify anything. Okay, so cos of 140 degrees all squared means cos 140 degrees all squared. Okay, so that's the same for tan 40 degrees. What that means is tan 40 degrees all squared. Okay, so you don't have to write out this line in your working, but I'm just doing it so that you all remember what these squares mean. Okay, and of course, if you are squaring something, whether you square a positive or a negative, you'll always end up with a positive. So you don't have to do the thinking of which quadrant you're in and whether that will be positive or negative, because your final answer will always be positive. Okay, but I'm a stickler for detail, so I will, in my bracket, keep the correct sign necessary. Okay, so cos 140 degrees is in the second quadrant, so we can rewrite 140 as 180 minus 40 degrees. Okay, then I have tan 40. Okay, so 40 is already an acute angle. We could write tan 40 as sine 40 over cos 40, so that might be useful to us, but for now I'm just going to leave it as is until we know what's happening in these angles, these trig functions, sorry. Right, so cos 220 degrees, 220 is in the third quadrant where we write our angles as 180 degrees plus whatever takes us to 220, which is 40. And then I have sine 50, okay. Now, sine 50 is already an acute angle, so I could leave it like that, or I could also take it to the co-function, okay, with the angle's complement. Right, let's do the reduction and see where that takes us. So, just notice how I don't know exactly where it's going to end. You just need to look at it carefully and try stuff. And remember that you have the identities and the reduction formulae at your disposal. Okay, so if we look at the first bracket, okay, second quadrant, this reduces to negative cos 40 degrees all squared minus, then I have the tan 40 degrees squared, okay, then this cos in the third quadrant reduces to negative cos of the acute angle, okay, and then I have sine 50, okay. Now, what I am seeing is that if I were to change this to its co-function, okay, which would take me to cos 40, then I would have cos 40 times cos 40, which is cos 40 squared, which if I were to write the tan as sine over cos, I would actually be able to cancel the cos. So what I'm going to do is change this sine 50 to its co-ratio. Now you can skip the step of writing, but I'm going to do it. So while the angle is still the same value, I keep the same trig function. Only once the angle changes do I change it to its cofunction. Okay, so negative squared gives me positive. So this is cos 40 degrees all squared. Okay, minus, now I'm going to write tan 40 degrees all squared as sine 40 degrees over cos 40 degrees using the quotient identity. And of course, this is all squared. Okay, then I'm multiplying by minus, so that's going to make this a plus. So I have cos 40 degrees times, now this 90 degrees indicates to me that I must take this to its cofunction of the acute angle, so it goes to cos 40 degrees. So here I have cos 40 times cos 40, it's cos 40 all squared, which I can cancel with the denominator. So I'm left with cos 40 degrees all squared plus sine 40 degrees all squared. And here we have the square identity. So remember, the square identity is sine angle all squared plus cos angle all squared equals 1. Okay, here of course it's just in the opposite order, but that doesn't matter. Okay, 2 plus 3 is the same as 3 plus 2. So this is the square identity which takes us to 1.